performance measures for multi-class classification. So now that we have a way to do multi-class classification, we need to develop some performance metrics for it. Evaluating a binary classifier was pretty easy using a 4x4 confusion matrix. And so here our confusion matrix is going to grow. We can build these confusion matrix just by calling the command in sk.confusion underscore matrix. The X didn't make it, but that's okay. Function similar to what we've done in previous steps, right? And we get a confusion matrix that looks like this. This is a confusion matrix that I got for the entire data set. So, we're looking at like 6,500 classified digits. And what you'll see is that they're mostly classified correctly, right? So again, if you're trying to sell a product, this might be a great confusion matrix to show someone, because basically it lights up down the middle and everything else is purple. No issues whatsoever. However, that's not really the honesty of what's going on here. So one thing that I like to do when building these is I like to just take out the center row. It's great that you can classify things right, but I'm typically interested in why do things fail. And so here I've normalized it and taken out my top row, and now I can see clearly what is miscalculated. And it looks like the most common thing that we have are 9s classified as 7s. So that might make sense, right? I have a 9 and it kind of looks like a 7, maybe starts to look like that. Remember that it's not looking at the actual image, right? It's looking at the features, and those features are just the intensity of the pixels. So one way to think about it is that the pixels in this location might be closer aligned to the pixels in this location on a 7 and a 9. And then from this, we can also look at, let's take a look at some other ones that are kind of misclassified. It looks like 3s and 5s are still going to be an issue here. So that's another issue. Here's our 3, and here's our 5. So those are pretty highly misclassified. And then typically it'll be symmetric. So an actual 3, is often estimated as a 5. So sometimes you get 5s estimated as 3s and 3s estimated as 5. What I find unique here is that 7s are not actually estimated as 9s a whole lot, right? I mean, they are, but compared to how often 9s are estimated as 7s is quite fascinating, right? So it kind of seems to be a one-way failure mechanism. And you can see some other patterns here kind of across the axis. So 9s and 4s, 8s and 5s, and then 5s and 8s, 4s and 9s, 8s and 3s. 8s are just kind of a mess. And you can see that in that this entire row looks pretty highlighted, and that entire row looks pretty highlighted. But 8s and 4s are pretty good. 8s and 4s are pretty good. So 8s just get confused a lot with 1, 2s, and 3s and 5s. So the confusion matrix is helpful for you to figure out where your mechanism is failing. And then another good thing to do is to dive a little bit deeper and to take a look at the individual failure mechanisms. So if we do that, went through the data set, and I pulled out things that were misclassified, right? So I have 3s correctly classified as 3s. So all of these 3s look pretty good. So let's compare 3s and 5s. That's what we're doing here, because 3s and 5s were kind of commonly interchanged both ways. And now I've got incorrectly classified as 3s. All of these are supposed to be 3s. And then I think they're all 5s, although I don't think I explicitly called it. It's just that most 5s are incorrectly classified as 3s. I can't tell you what that is. I agree. So, sometimes the data is just a little bit vague. The rest of these, I can get, this one's cut off. There's only so much compassion you can have on a machine for missing that one. And then we've got digits classified as fives. So these are incorrectly classified as fives. This one, I don't understand why. These look like pretty good threes to me, honestly. This one here, I could get you that that's a 5. This one here, I could see it, right? It's kind of got this flat top to it. This one just looks weird to my eye, which again is not how the classifier sees it. The classifier sees it as the number of pixels. That I don't. They look pretty clear to threes to me. This one kind of looks like a 5. And I'm not at all saying a regularized linear classifier trained with stochastic gradient descent is the world's best model. But in terms of understanding how machine learning works, there's a lot of value in digging deeper into this. So something to think about. That one's a 3, but only in the context that I know it's either a 3 or a 5. If you just showed me that squiggly line, I wouldn't be able to read it. And all of these are 5s and correctly classified as 5s, and they look pretty good. All of them except this one, which I'm fascinated that that one made it to the 5. And this one was incorrect, was not classified. Some of these look pretty close to me, so just kind of interesting to think about the 3-5 confusion, right? One other thing that you can do also is a common step that we'll use to improve figures is you could take a 3 and you could rotate it, right? Rotate it 10 degrees and add it to the data set. You could rotate it left. You could take a 3, you could rotate it to the left, sorry. First time would be rotating it to the right. And then you could supplement your data set. You could augment your data set because some of these are just kind of 3s written at an angle. I don't know if anyone, when they write, people will shift their paper to an angle to write, but sometimes when you're writing a letter, you just try to do it flat. So things to think about, kind of the context of how the data is collected, how people write, think about the data.